this video, we're gonna learn about different types of relation, equivalence class and partition. Different types of relation. There are basic 7 types of relation: reflexive, irreflexive, symmetric, asymmetric, antisymmetric, transitive and circular. Now based upon this basic types of relation, we again have 2 types of relation: equivalence relation and partial order relation. Let's begin with different types of relation. Before beginning, let's understand or consider a binary relation R on a set which is subset of Cartesian product of that set. So my relation is a subset of Cartesian product on the same set. For all of this type of relation, we are assuming the same consideration. First type of relation, reflexive relation. Now to make our relation reflexive relation, we should have self-order pair. Order pair which should have on the both side, first place and second place, the same element, and for each and every element of your set you should have such kind of order pair. Then and then only your relation is reflexive relation. For example, my set is having element 1 2, relation is 1 1 2 1. This is not reflexive relation because all the possible order pair for all the elements, that is 1 1 2 2, but 2 2 is missing in my relation, so this is not reflexive relation. Second example of relation 1 1 2 1 and 2 2. Now here all possible self order pair for all the elements in my set is 1 1 2 2, both are present, so this relation is reflexive relation. Next type of relation is irreflexive relation. This is exactly opposite as that of your reflexive relation. Now here, for each and every element of your set, you should not have self-order pair. If at least one is also there present, then your relation is not irreflexive relation. Let's take one example. A is set which is having 2 element 1 2, and relation R is 1 1 1 2. Now here I am having one entry which is self-order pair, but what the thing I want, I should not have even a single entry for any of the elements order pair, self-order pair in my relation. So this relation is not irreflexive relation. Second example, 1 2 and 2 1. Now here in this relation I don't have the self-order pair. That are all possible order pairs for my set, that is 1 1 and 2 2. Both are missing, so this set is irreflexive relation. Now let's understand different types of relation, that is symmetric, asymmetric and antisymmetric. Now for understanding this concept, what assumption we are making for simplicity, let's assume that if I am placing my order pair A, B in front of mirror, what the mirror image I will get for that will be B, A. And if I will place A, A in front of a mirror, what the mirror image I will get, that will be A, A. Now based on the concept of this mirror image or our assumption on mirror image, we are having these 3 different types of relation: symmetric relation, asymmetric and antisymmetric relation. If for order pair A, B and A, you are having for each and every element in your relation, its a mirror image is present. For all the elements present in relation, their mirror image is present, then that relation is symmetric relation. For every pair in your relation A, B and A, you are not having its mirror image in your relation, then that relation is asymmetric relation. Antisymmetric relation. Now for some of the order pairs you are having their mirror image in the relation itself. Now what kind of this? For A, B you are not having. For order pair A, B, its mirror image is not present in your relation. But for order pairs where A, or first and second element both are same, for such elements you are only having their mirror image in your relation, then that relation is antisymmetric relation. Let's take one example. For symmetric relation, my set is 1 2 3 and relation is 1 2 2 1 2 3 and 3 2. Now for checking whether our relation is symmetric, what we will do, we will take one by one each order pair. For 1 2, what I should have for making this relation symmetric relation, for each and every element inside my relation, its mirror image should be present in the relation itself. For 1 2, mirror image is 2 1, that is present in my relation. Okay, for 2 comma 1, the mirror image is 1 comma 2. That is also present in my relation. For 2 comma 3 pair, the mirror image will be 3 comma 2. That is also present in my relation. For 3 comma 2, the mirror image is 2 3, which is also present in my relation. Means for each and every element in my relation, their mirror image is present inside the relation itself, then my relation is symmetric. So this relation is symmetric relation. Now let's take another example, 1 comma 1, 2 comma 1 and 3 comma 3. For 1 comma 1, mirror image is 1 comma 1 present in the relation. Okay, for 2 comma 1, the mirror image is 1 comma 2, but this mirror image, this element is not present in my relation. So whole this relation will become not symmetric relation. Next type of relation is asymmetric relation. Now for making a relation asymmetric relation, for each and every pair of order pair, you should not have their mirror image in your relation. For example, set A is 1 2 3 and relation is 1 2 2 1 2 3 and 3 2. Now we will check for 1 2, I should not have its mirror image in my relation. For 1 2, mirror image is 2 1, but that is present in my relation. So I will stop further checking whether for other elements I am having their mirror image. That mirror image is present, so my whole relation will become not a symmetric relation. Let's take another example of relation 1 comma 2 and 2 comma 3. For 1 comma 2, mirror image is 2 comma 1. What I don't want this entry in my relation. Okay, that is not present in my relation. For 2 comma 3, the mirror image is 3 comma 2. What I don't want this entry also in my relation. Then I have completed and I found that for each and every element, their mirror image is not present in the relation. So this relation is a symmetric relation. Next type of relation is anti-symmetric relation. Now in this type of relation, for some of the pairs, you will have their mirror image in relation, but for some of the types you don't have their mirror image in the relation. For example, set A is having elements 4 5 6 and relation R is 4 4 4 5 5 4 5 6 and 4 6. Now in this, what I want, only for elements order pair where both the places are having same number. Apart from that, I should not have for the rest element their mirror image in my relation. So except this entry, for 4 5, I don't want its mirror image in the relation, but that is present in my relation. So this relation is not anti-symmetric relation. Next type of relation is 4 4 and 5 4. Now for 4 4, their mirror image is present. Okay, no problem. For 5 4, I don't want its mirror image in my relation. That is not present. Means I completed and I checked that for every pair A comma A, their mirror image is present in my relation, and for the pair A comma B, its mirror image is B comma A, which is not present in my relation. So this relation is anti-symmetric relation. Next type of relation is based on transition, that is transitivity relation and circular relation. Now both this type of relation are based on transition concept. If in your relation you are having two pairs A comma B and B comma C, if such both pairs are exist, then the transition will be A comma C. Means for each and every elements in your relation of type A comma B and B comma C, you should have transitional element, that is A comma C must be present in your relation, then only your relation is transitive relation. For example, A is 1 2 3 and relation 1 1 2 2 2 1 and 1 2. Now we'll take example where first place and second place of order for order pair is same. Now here, if we will take this example where second place of first order pair and first place of another order pair is same. Now for 2 1 and 1 2, their transition will become 2 2. For this pair also, if we will reverse this, then we will have 1 2 and 2 1. The transition will be 1 1. Means for each and every element we have checked and found that their transitive element is present in my relation. So this relation is transitive relation. Next example is 1 1, 1 2 and 2 1. For this 1 2 and 2 1, I have checked the transitive relation is 1 1, that is present in my relation. But if I will change the order of this 2 1 and 1 2, For A comma B and B comma C, you should have A comma C pair. Means from this, what is the A comma C pair I am getting? That is 2 comma 2. If I will try to cut this, I will get 2 comma 2. But 2 comma 2 is missing in my relation, so this relation is not a transitive relation. Next type of relation, that is circular relation. Now this is exactly just opposite as that of transitive relation, where for each and every pair of A comma B and B comma C, we are checking A comma C pair. If you will try to check its mirror image, then that will become C comma A. Means for each and every pair of A comma B and B comma C in your relation, you should have transitive element C comma A in your relation itself, then that relation will become circular relation. For example, set 1, 2, 3 and relation 1 comma 1, 2 comma 2, 2 comma 1 and 1 comma 2. For this example, transitive relation will become 2 comma 2, that is present in my relation. For 1 comma 2 and 2 comma 1, transitive relation is 1 comma 1, that is also present in my relation, so this relation is circular relation. For 1 comma 1 and 1 comma 3, the transitive element will be 3 comma 1, which is not present in my relation, so this relation is not circular relation. Now based on the combination of these 7 types of basic relation, we are having 2 types of relation: equivalence relation and partial order relation. Equivalence relation, any binary relation which is satisfying these 3 property, reflexive, symmetric and transitive, that will be called as a equivalence relation. For example, set A is having element 1, 2, 3, 4 and relation R is 1, 1, 1, 3, 2, 2, 2, 4, 3, 1, 3, 3, 4, 2 and 4, 4. Now I should have all these 3 properties satisfied by my relation, then and then only my relation will become equivalence relation. Now go for checking one by one all of this property. Reflexive relation. A relation is reflexive when for each and every element in your set you are having its self order pair. Means I should have 1 comma 1, 2 comma 2, 3 comma 3 and 4 comma 1, 4 entry in my relation. All these entries are present in my relation, then 1 comma 1, 2 comma 2, 3 comma 3 and 4 comma 4. Then this relation is reflexive relation. For making my relation symmetric relation, I should have for each and every element in my relation its a mirror image in the relation itself. Then my relation will become symmetric relation. Now I am checking for each and every element. For 1 comma 1, mirror image is that element itself, that is present in my relation. For 1 comma 3, the mirror image will be 3 comma 1, that is present in my relation. For 2 comma 4, mirror image is 4 comma 2, that is present in my relation. For 3 comma 1, mirror image is 1 comma 3, which is also present in my relation. Now I checked for each and every element, their mirror image is present in my relation, so this relation is symmetric relation. Last property is a transitive relation. For element which is of type A comma B and B comma C, I should have the transitive element, that is A comma C, in the relation itself, then my relation will become transitive relation. Now I tried for such a pair. For let's take example, that is for 1 comma 3 and 3 comma 1, transitive element will be 1 comma 1, that is present in my relation. For element 2 comma 4 and 4 comma 2, transitive relation will be 2 comma 2, which is present in my relation. For pair 2 comma 2 and 2 comma 4, transitive relation will be 2 comma 4, that is present in my relation. Means I checked for each and every possibilities, all its transitive relation are present in the relation, so this relation is transitive relation. Now this relation is satisfying all of these 3 properties, that it is reflexive, symmetric and transitive. Hence this relation is equivalence relation. Next type of relation is partial order relation. Now in equivalence relation and partial order relation, the only difference in this second property, both are reflexive and transitive, but equivalence relation is symmetric and partial order relation is anti-symmetric in its property. The same example, we will take another example. Set A is having element 1, 2, 3, 4. Relation R is having element 2, 1, 3, 1, 3, 2, 4, 1, 4, 2, 4, 3, 1, 1, 2, 2, 3, 3 and 4, 4. Now for making this relation reflexive relation, I should have 1, 1, 2, 2, 3, 3 and 4, 4 in my relation. all they are present. So this relation is a reflexive relation. For making this relation anti-symmetric relation, I should have only A comma A mirror image for A comma A pair, that is A comma A itself, but for the rest, that is for elements which is of type A comma B, means where in the order pair their first and second element are different, then their mirror image is B comma A, then that should not be present in my relation. So I am checking the same. For 2 comma 1, I am not having its mirror image, that is 1 comma 2 in the relation. Okay. For 3 comma 1, I should not have 1 comma 3, that is its mirror image in the relation, that is not present. Okay. For 3 comma 2, the mirror image is 2 comma 3. 2 comma 3 should not be present in my relation. Okay, that is not present. For each and every element, I checked and I found that for each and every element, its mirror image is not present in the relation when the element is of type A comma B, and for all the elements which is of type A comma A, for example 1 comma 1, their mirror image is present in the relation. So this relation is antisymmetric relation. Now to check transitive property, I should have transitive element for A comma B and B comma C pair in the relation itself. For example 3 comma 2 and 2 comma 1. Here transitive element will be 3 comma 1, that is present in my relation. I checked for each and every possibility and I found that their transitive element is present in my relation. So this relation is partial order relation. Equivalence class. Equivalence class is measured on the equivalence relation element. If your set element are, for example, if my set element is 4, 5, 6, 7, I will have equivalence class for 4, 5, 6 and 7. Not for the element inside the relation. Okay, not for order pair inside the relation. Equivalence class is measured for elements of your set. And how we measure this equivalence class? If you are having order pair in your relation A comma B, then first element is always your equivalence class, and the element which is present on the second place, that is the member of that equivalence class, that is the one of the entry inside the set of your equivalence class. Now here is the example. Set A is having element 4, 5, 6, 7. Relation R is having element 4, 4, 5, 5, 6, 6, 7, 7, 4, 6 and 6, 4. Now step by step, if I will take order pair, now first element is equivalence class and second element in the order pair is its element. Same way I have calculated for each and every element. Now what I will do, I will check whether this 4 equivalence class is appearing anywhere again. Now this is appearing here, so I will try to combine its right hand side, that is set element. Now this will become 4 comma 6. In the same way for another, that is 6 is appearing more than once and which is having element 6 here and 4 here. So equivalence class of 6 will have element 6 comma 4. Further, what I will do, I will check whether this portion is appearing for any other equivalence class exactly the same. 4 comma 6 and 6 comma 4 both are the same. So equivalence class of 4, 6 is having element 4 comma 6. For 5, the equivalence class is 5. For 7, the equivalence class is 7. The shortcut method can be wherever in the order pair. Suppose I am trying to find the equivalence class of 4, so I will check where in the order pair wherever I am having 4 element. So in this 4 is coming, so along with the 4, what are the other elements I am having? So here 4 is coming, here 4 6 is coming and 6 4 is coming. Now for equivalence class of 4 and 6 will be 4 6. In the same way, equivalence class of 5. Now 5 is appearing only one time. So 5 is appearing with 5 itself. So equivalence class of 5 will be the same element. Equivalence class of 7 will be the same element. The next topic is partition. Partition of set S is collection of disjoint non-empty subset, and that is represented by all the possible subset which are combining, which are making your whole set. That is called as a partition. The property is that in two different partition or in two different set, you should not have there any element which is coming in both the set, means their intersection should be null set, and the all of set subset, when I will try to unite or perform union on that, I will get whole the set. For example, set A is having element 1 2 3 4 till 8. Partition P1 is having element 1 2 3 4 1 3 5 6 7 8. But here 1 and 3 element are appearing in both the partition subset, so that cannot be present. It should be present only in the one subset. Hence, this is not the partition. Another example of partition, that is 1 3 5 7 2 4 and 6 8. Now here inside each and every subset, every element is different. Okay, now 1 3 5 7, any of the element is not appearing in any other subset. And also when I will try to perform union of all of this, so I am covering all the elements of my set. So this set is partition of my given set.